Namaskar students. We are discussing about sinusoidal steady state analysis, and in today's lecture we are going to start our fresh topic, that is mutually coupled circuit. So up till now whatever we are considering that a conductively coupled circuit, because the one loop affect the neighboring loop through the current conduction. Okay, so whatever the branch current that we have find up till now using mesh analysis and nodal analysis. What is mutually coupled circuit? So when two loops with or without contacts between them affect each other through the magnetic field generated by one of them, they are said to be magnetically coupled. Now as far as the basic example of magnetically coupled circuit is given by a transformer. Okay, it is an electric device designed on the basis of the concept of magnetic coupling. Now it uses a magnetically coupled coil to transfer energy from one circuit to another circuit. So it is not required that both the circuit are connected, but if let us consider what is transformer. Transformer is nothing but your primary winding and your secondary winding are not connected conductively, but they are connected magnetically. That is why we can say that transformer is designed on the basis of magnetic coupling principle. Okay, so the exchange transfer of energy between this coil and this coil is by magnetic field. So transformer are we know that it is the key circuit element of a power system network, because whenever we are trying to step up or step down either voltage or current, we need to have transformer in the circuit. Okay, and in transformer is basically working on the principle of magnetic coupling. Now before going to understand magnetically coupled circuit, we have to go through what is the mutual inductance and what is the self inductance. So we know about self inductance, but we don't know about mutual inductance. So when two conductor or coils are close proximity to each other, and the magnetic flux caused by the current in one coil links with another coil, thereby including voltage in later. So here you can see an example of coil that is connected to a current source, and this current is going to flow through the inductor. In that case the flux is going to be generated, and you can see this flux, and due to the rate of change of flux there will be voltage induced, and that is given by V. So such kind of phenomena is generally known as mutual inductance. Now let us first consider a single conductor that is shown in the figure, and the number of turns in this inductor is, let's say it is n number of turns. So when current I flow through the coil, the magnetic flux phi produce around it. Okay, so here we have taken that there is only one coil that having a n number of turns, and the generated voltage is V and flux is given by phi. Now as far as the value of V is concerned, according to Faraday's law, we can find that the voltage V induced in a coil is proportional to the number of turns n and the rate of change of magnetic flux phi. So it is given by V is equal to n multiplied by d phi by dt. Okay, it means V is directly proportional to the rate of change of flux. Now we know that flux is produced by current I, so that any change in flux is basically caused by the change in current. Okay, so we can represent this d phi by dt as d phi by di multiply by di by dt. So mathematically we can say that we are multiplying this equation by di and divided by di, but this portion d phi by di is the change in phi that is caused by the change in current. So this equation can be also rewritten in this form. So you just put the value of d phi by dt, that is d phi by di, multiply by di by dt, and you will get this equation. Okay, now this term n multiply by d phi by dt is nothing but your inductor L. So put the value of L right here, and you will get that the voltage induced in case of an inductor, that is given by V is equal to L di by dt, and that is the voltage and current relationship in case of an inductor. Okay, now this inductance is commonly called the self-inductance because it relates the voltage induced in a coil by the time varying current in a same coil. So in figure that we have already shown that there is only one coil is right here. Okay, there is no second coil. So whatever the EMF is induced or the voltage is induced in a coil by the time varying current in the same coil, no other coil. That is why it is called self-inductance, and the voltage is called self-induced voltage. Okay, now let us consider another example where we are using two coils rather than using single coil. So the first coil having self-inductance L1 and another coil that is having self-inductance L2. They are close proximity with each other. Now the number of turns in coil 1 is N1, while the coil 2 has number of turns N2, while 2 has N2 turns. Now for the sake of the simplicity, we are assuming that the second inductor is initially carrying no current. That is why the current source is supplied right here. So current in this coil will be, let's say it is I1. Okay, due to there will be some generated flux right here. So we can say that the magnetic flux phi 1 emanating from coil 1 has two components. The first component is phi 11, and that will link only coil 1. Okay, you can see that the first component will link only coil number 1. Now another component is phi 12, and that will be linking to coil number 2. Okay, this is your coil number 1, this is your coil number 2. So another component is nothing but the generated flux through coil 1, and that will be linked to coil 2. That is why it is given by phi 12. Okay, so total flux phi 1 can be written as phi 11 plus phi 12. Okay, phi 11 is that links only coil 1, and phi 12 is that links both the coils. Okay, so you can understand when current I1 flow through this coil 1, in that case the generated phi 1 can be rewritten as phi 11 plus phi 12. Now the two coils are physically separated and they are said to be magnetically coupled. So the voltage induced in a coil 1 can be written as N1 d phi by dt. Okay, we can find Faraday's law of electromagnetic induction, that the induced voltage is nothing but directly proportional to the rate of change of flux. So V1 is equal to N1 d phi 1 by dt. Okay, same you can put the change in flux is nothing but due to the change in current. That is why we can represent this equation as d phi by di multiplied by di1 by dt, and this term is nothing but your L1. Okay, self-inductance L1 multiplied by di1 by dt. Okay, so when current is in the coil 1 is I1, and L1 is the self-inductance of coil 1. Now this is nothing but the total flux phi 1, but phi 12 that links only coil 2. So the voltage induced in a coil 2 will be written as V2 is equal to N2 d phi 12 by dt. So N1 is equal to, same you can rewrite this equation and just multiplying and dividing by di1, and this term N1 multiplied by d phi 12 by di1 is nothing but your M21 multiplied by di1 by dt, and M21 is the mutual inductance of coil 2 with respect to coil 1. Okay, so whenever we are finding the value of induced voltage when the current through this second coil is 0, in that case the induced voltage in second coil can be represented by M21 di1 by dt, where M21 is mutual inductance of coil 2 with respect to coil 1. Now this subscript to 1 indicates that inductance relates the voltage induced in coil 2 due to the current in coil 1. In vice versa, if M12 is there, it means that the voltage induced in coil 1 due to the current in coil 2. Now consider that the I2 current is flowing through coil 2. So let us assume that I2 current is flowing through coil 2. In that case, the magnetic flux phi 2 emanating from coil 2 has again two components. The first component is phi 22 that will links only the coil, that is number 2 in this case. Another component is the component that is phi 21 that will links both the coils, it is coil number 1 and coil number 2. So we can write the total flux phi 2 when the current is flowing in coil 2 is given by phi 21 plus phi 22. Okay, it is the same as before. Okay, so phi 22 is equal to phi 21 plus phi 22. Now since the entire flux phi 2 links with coil 2, that is why the voltage induced in a coil 2 can be written as V2 is equal to N2 d phi 2 by dt. Okay, so if you want to find the voltage across this coil, so voltage across this coil can be the rate of change of flux will be considered as phi 21 plus phi 22, that will be phi 2. That is why we have written d phi 2 by dt, because phi 2 is the flux that links to coil 2. So your first component, that is phi 21, and your second component, that is phi 22, both link with this coil number 2. That is why the here we have written phi 21, but in this case of V2 we are writing phi 2 only. Okay, again you can rewritten this equation in this form and put the value of N2 d phi 2 by di2 is equal to L2. So I2 is the current in coil 2 and L2 is the self inductance of coil 2. Now the phi 21 flux that links with only coil number 1. Okay, so the voltage induced in coil 1 can be written as V1 is equal to N1 d phi 21 by dt. So that can be rewritten as N2 d phi 21 by di2 multiplied by di2 by dt. Okay, so all these things are repeated, that is why I am not going to explain each and every time. If you have any doubt, in that case you can contact me anytime. Okay, now this term again N2 multiplied by d phi 21 by di2 is nothing but your mutual inductance M12. Okay, so M12 is the mutual inductance of coil 1 with respect to 2. So I hope you understand this. M21 and M12 both are a different thing. Okay, so you can understand that whenever it is coil M12, in that case the mutual inductance of coil 1 with respect to coil number 2, it means that the current is flowing through coil number 2 in this case, and coil number 1 has the induced EMF that can be given by M12 di2 by dt. Now the mutual impedance is the ability of one inductor to induce a voltage across a neighboring inductor, and then that is generally measured in terms of Henry. Also the unit of inductor is nothing but Henry. Now although the mutual inductance that is M is always a positive quantity, but the mutual voltage that is M di by dt, it might be negative or it might be positive, just like your self-induced EMF, that is L di by dt. Now unlike your self-induced EMF, whose polarity is determined by the reference direction of the current and the reference polarity of the voltage, and that can be easily understandable by your passive sign convention. But the polarity of mutual voltage is not easy to determine because the four terminals are involved, the two terminals of one coil and the two terminals of another coil. That is why the polarity of mutual voltage is not that easy to determine. So the choice of the correct polarity of your mutual voltage is made by examining the orientation of your coil 1 and coil 2. Okay, and by applying Lenz's law along with the right-handed rule, we can find the sign of your induced voltage, mutual induced voltage, that is either positive or negative. Now, since it is not easy to show the construction details of the coil on a circuit, that is why we are applying the dot convention in circuit analysis. Now, by this convention method, the dot is placed in a circuit at one end of each of the two magnetic coupled coil. For what? To indicate the direction of magnetic flux if current enters that dotted terminal of the coil. So we're going to understand what is dot convention and how we are going to apply it into find the value of mutual voltage, either it is positive or negative. So let us take an example that this circuit is given right here. You can see the one coil is right here, that is coil number 1. The second coil is right here, that is coil number 2. The current flowing in this coil is given by I1 and here it is given by I2. Here already the dots are mentioned that the current going into the direction of dot only. Same current is also going from the dot only right here. So whenever current flow through this coil, there will be some flux generated, and that have two component. One component that is only linked with that coil only, that is phi 11. Another component will be phi 21. It means the flux that links to coil 2 due to the current in coil 1, that is given by phi 21. So phi 1 can be written as phi 11 plus phi 21. Same way the current flowing through this coil will be I2. In that case, the flux that can link only to coil 2, that is given by phi 22, and another component that can be given by phi 12. Here the direction of flux is very important. If you see that the physical foundation of your coil, you can see this can be the direction of your coil, and if you curl your finger in this direction, in that case your thumb will be on upward direction, and that is why the direction of your flux will be upward direction. Same way you can apply in this second coil. You can see your direction of your coil will be this, and if you curl your finger in this direction, the direction of thumb will be in downward direction. That is why your direction of flux will be, again it is clockwise. Here also it is clockwise, again here it will be clockwise. So that is why your phi 21 and phi 12 both will be in the same direction. Okay, now given a circuit, the dots are already placed besides the coil, so that we need not to bother about how to place them. Now the dots are used along with the dot convention to determine the polarity of the mutual voltage. So how we can define the polarity, that is of the mutual voltage M12 and M21, that we are going to understand. But here the dots are already placed, so we don't have to worry about how to place them. Okay. Now what is the dot convention? So it can be explained as follows, that if current enters at the dotted terminal of one coil, the reference polarity of mutual voltage in the second coil is positive at the dotted terminal of the second coil. So I hope it is very clear that if let's say in this coil, let's say it is an inductor or coil 1. So if current enter at the dotted terminal of one coil, let's say the direction of current is this and dot is placed right here. So if current enter the dotted terminal of one coil, it means we are talking about this example, and the reference polarity of mutual voltage, let's say in this coil the reference polarity is plus and minus. In another coil, let's say the reference polarity of mutual voltage in the second coil is positive at the dotted terminal. Let's say here it is positive and dot is right here. Okay, this is V2 of the second coil. Okay, so if current enters at the dotted terminal of one coil and the reference polarity of mutual voltage in the second coil is positive at the dotted terminal of the second coil, in that case the mutual voltage will be positive. Now alternatively, if the current leaves the dotted terminal of the one coil and the reference polarity of mutual voltage in the second coil is negative at the dotted terminal of the second coil, we are talking about that if the dot are placed not here but right here, and here the dotted current will be leaving from the dotted terminal. Same way the current in here right here, let's say it is I2, and that is leaving from this dotted terminal. In that case the mutual voltage will be positive. Now thus the reference polarity of mutual voltage is generally depends on the reference direction of inducing current and the dots on the coupled coils. Now let us try to understand all these rules in using some examples. So let us consider this coil 1 and coil 2. You can see that dots are already placed. The current that is flowing through this coil 1, that is given by I1. The mutual inductance can be represented as M. The voltage induced, that is mutual voltage, is equal to M di1 by dt. So the sign of mutual voltage V2 is determined by the reference polarity of V2 and the direction for I1. Okay, so reference polarity of V2 is given by, here it is plus and here it is minus. The direction of current is this. Okay, so since we can see that the I1 is enter at dotted terminal, you can see that I1 is entering at dotted terminal of coil 1 and V2 is positive at the dotted terminal. You can see at the dotted terminal it is positive, so the sign of mutual voltage will be positive. So here you can see that is M di1 by dt. Okay, if the polarity is reversed, let's say it is in this case the minus and plus will be there, your value of V2 will be minus M di1 by dt. Okay, so two things you need to keep in mind, that the direction of current at dotted terminal and your polarity of voltage. Okay, so here you can see your current is going to enter at dotted terminal and your polarity at dotted terminal is positive. That is why the induced voltage will be positive. Okay, very simple. Now let us consider this case. Now since you can see that your same figure, the dotted terminal current is entering, but at this terminal, that is dotted terminal, at that point your polarity of voltage is negative. That is why your induced voltage V2 can be given by M di1 by dt. You can see that since I1 enter at the dotted terminal of coil 1 and V2 is negative at the dotted terminal of coil 2, that is why the mutual voltage is written as minus M di1 by dt. Okay, that we have already discussed. Now the reasoning applied to the previous two circuits can be used to understand the following two circuit as well. You can see that same, this is coil 1, the dot is already placed. Here you can see the coil number 2, the direction of current. Here you can see the current is not entering at dotted terminal but it is leaving from dotted terminal. Okay, so whenever your current is leaving from dotted terminal, in that case whatever the sign in another coil. If at dotted terminal the sign is plus, in that case your induced voltage will be minus. If at dotted terminal the sign is negative, in that case your induced voltage will be plus. Okay, when your current will be leaving from the dotted terminal. So in first case we have seen when your current is enters at dotted terminal. Here we are seeing that your current is leaving from the dotted terminal. So in first case, whatever the sign at dotted terminal will be your sign of induced voltage. If plus, then your induced voltage will be plus. Here in case of second, whenever your current is leaving from dotted terminal, in that you can see your current is leaving. That is why whatever the polarity at dotted terminal will be reversed. So here it is plus, that is why the induced voltage will be minus M di2 by dt. Here you can see this another example. So here also current is leaving from dotted terminal, and at the dotted terminal the polarity is minus, that is why your voltage will be plus M di2 by dt. Very simple. If you just keep these two things in mind, this induced voltage, mutual induced voltage, polarity can be easily found out. Now consider a series connection of inductor where two inductors are connected in series. You can see here also first coil, the direction of current into the dotted terminal, same here. So in that case the total inductance, that is given by L1 plus L2 plus 2M because it is the series aiding connection. Same way, whenever your current is the connection is in series, but the dot is placed here when current is entering to dotted terminal. In second coil the current is leaving from dotted terminal. In that case your inductor total inductance is given by L1 plus L2 minus 2M, and that is due to the series opposing connection of inductors. Okay, now that we know that how to determine the polarity of mutual voltage, and we are prepared to analyze the circuit involving the mutual inductance, now consider the following example. That here it is the first mesh. You can see the second mesh is here. The mutual inductance, that is given by M. In first coil there is a resistance, inductance, same resistance R2, inductance L2. So now first apply the KVL to coil number 1. So if you apply, then V1 can be given by V1 is equal to the voltage drop across this resistor, that is given by I1 multiplied by R1. The voltage across this inductor can be given by L1 di1 by dt, and the mutual voltage that can be given by M di2 by dt. Here the sign is positive because your current is entering at dotted terminal. Same way you can see your current is entering at dotted terminal, and polarity is plus and minus. Same here, plus and minus, that is why the sign will be plus. You can convert this time domain into frequency domain using Laplace transformation. Okay, now same way you can apply the KVL in coil 2, then it will be V2 is equal to I2 that and multiply by R2, that is voltage drop across this resistance, and voltage across this inductance can be given by L2 di2 by dt, that is self-induced EMF, self-induced voltage, and that is mutual induced voltage. Here also the sign will be same because current is entering, and here also the current is entering through dotted terminal. Now let us discuss another example. So here you can see that your current in this direction I1 dot is placed right here, and in second coil dot is placed at the same point, but the direction of current is also the same. Okay, so here you can see current is entering at dotted terminal, but in this case the current is leaving from dotted terminal. So then the polarity here it is plus minus plus minus. So you can clearly see that whenever we try to write down the equation of voltage, so apply the KVL in this loop. In this case directly we are writing in frequency domain, so V is equal to nothing but Z1 multiplied by I1. So we have taken this I1 common, that is by Z1 multiplied by I1 plus j omega L1 multiplied by I1. Now the whatever the mutual voltage that is going to generated, the sign will be minus, because here it is the your current is going inside the dotted terminal, but here it is going outside the dotted terminal. That is why the sign will be minus, because at the dotted terminal the polarity is plus, that is why we have to take minus. The same way, if you apply the KVL in second loop, it can be written as 0 is equal to ZL plus j omega L2 multiplied by I2 minus j omega I1. So here you can see the negative sign. Okay, so now let us consider one example. In that case we are interested to find the value of current I1 and I2 into this circuit. So same example, but here we are dealing with some values of inductor and capacitor. So now apply the KVL in mesh 1. In that case we get the equation that minus 12, that is the voltage source right here, plus the whatever the voltage across this capacitor, that is minus J4 multiplied by I1 plus J5 multiplied by I1, that is your self-induced EMF. Okay, self-induced voltage. But mutual induced voltage, that is J3 multiplied by I2. Now this is important thing, the sign of your mutual induced voltage. Here you can see your current is going inside the dot, inside a dotted terminal. Here it is leaving from dotted terminal, that is why sign will be negative. So it is equal to 0. Okay, so if you simplify this equation, you will get ji1 minus ji3 is equal to 12. Let's say this is equation number 1. Now you apply KVL into second loop, it will be the no voltage, so that is why 0 is equal to 12 into I2, that is 12 into I2 plus J6 into I2, that is your self-induced voltage, and mutual induced voltage is J3 multiplied by I1, J3 multiplied by I1. Here you can see that your current is leaving from dotted terminal, here it is entering from dotted terminal, that is why the sign will be negative. Okay, so let's say this equation is number 2. Okay, if you just simplify this equation, now you can put the value of I1 into this equation, and this equation will be in the form of I2. So from this you can find the value of I2, that can be 12 divided by 4 minus j, and if you convert in polar form, it will be 2.91 at an angle of 14.04 ampere. Okay, and by putting the value into another equation, that is this, if you put the value of I2 in this equation, you will get the value of I1, that is 2 minus J4 multiplied by I2, and in polar form it can be 13.01 at an angle of minus 49.39 ampere. Okay, so with this we are closing this lecture. I hope you understand how you can identify the sign of mutual induced voltage when two coils are magnetically coupled. Thank you so much. We will start new topic in next lecture. Thank you.